Well, hi. Dr. Scott Stevens again, this time talking about an idea called dispersion, and two of its more important and more common measures, standard deviation and variance. I was trying to think about how to get the idea of dispersion across to you, but dispersion is really just spread. The idea kind of came home to me, if you like, when I was looking at a tree similar to the one that you see below. It is loaded, I mean loaded with birds, and right now they're compactified. But now they're dispersing, they're spreading out. The mean position, the average location of those birds, doesn't change very much as they fly off. The ones on the left balance out the ones to the right, but their spread becomes much, much greater. What we're interested in this lecture is how can we measure that? If these birds get a few extra friends coming around and it's perching on a telephone line that looks like a number line, we can look at their positions and try to figure out how spread out they are. A simple measure is simply to look at the ones that are at the furthest outside. The bird on the left is about location 3 on my number line, and the bird on the right about 50. So the distance between those two numbers is 50 minus 3, or 47. There are 47 units of distance between the two end birds. And that's called the range. It's the simplest measure of dispersion, but not an especially useful one because it ignores all the birds in the middle, whether they're clustered or spread out. So we'd like a better measure. And the one that we usually use, or the ones that we usually use, are based on how far birds are away from the center of the action. And for the center of the action, usually we're talking about the mean. You can find the mean by imagining the birds are standing on a board like you see here, and then asking where we would have to put that board to make it into a teeter-totter that would stay level. Pretty clearly, where the teeter-totter's fulcrum is right now wouldn't work. Those birds would definitely weigh down the board on the right-hand side. So the triangle would have to move somewhere further over to the right, something like that. The balance point is what we're looking for, the point at which the teeter-totter would just remain level. So let's put our number line back on and see where that would be. Looks like about 23 on our line. We can talk about each bird's distance from the center. That's called, this guy here, for example, has a value of 11. If we look at how far a bird is from the mean, the location of the bird minus the mean, we get what's called the deviation for that observation, for that bird. Here it would be 11 minus 23, so that observation has a deviation of minus 12. And you could find the deviations for all the other birds as well. The further from the center, the larger in magnitude that deviation will be. What I really want to do, however, though, is to realize that since every bird has its own deviation, with the ones on the left being negative and the ones on the right being positive, I'd like to combine all those numbers in some way so that I would get a single number that represents the whole flock, the whole set. One obvious way to do that is to take all of those deviations and average them together. But it turns out that's a terrible idea. And the reason is that some of our deviations, as we've seen, are negative and some are positive. A negative 12 distance and a positive 12 distance from the mean average out to 0, but it doesn't mean that the two observations that we looked at were both sitting right on the mean. Well, this isn't hard to refine. How about averaging all the deviations but taking their absolute values first? That is, getting rid of the plus or minus signs on the numbers. This is actually a good idea, and the result is used. It's called the mean absolute deviation, or MAD, and you'll be seeing it more in 291 and also in 300. Let's see how it would work. Suppose I have 4 observations, 4 birds, and their distances from the mean are 8 to the left, 4 to the left, 4 to the left, and 16 to the right. Negative 8, negative 4, negative 4, and positive 16. What's the MAD? Drop the signs on these numbers and then just average them. And when you do that, you get 8. The interpretation of MAD is easy. It means on average, the birds are at a distance of 8 from the balance point, from the mean. But this isn't what we usually do. Instead, we do this. Average all the deviations, but square each of them before you average them. How would that work? Well, if we had the same deviations of the ones we talked about, we're going to take each of those deviations, square each one, multiply it by itself, and then average those squares. You're averaging 64, 16, 16, and 256, and when you do that, you get 88. Notice that the lion's share of this calculation comes from that 16. Although 16 is twice as big as 8, its square is much bigger than twice as big. So what do we do with this? Well, that calculation, that 88, is called the variance of our sample, or our population. And if you take its square root, you get what's called its standard deviation. So the variance is 88, and the standard deviation is 9.36, compared to the MAD value that we saw of 8. These are different measures of spread, And MAD is certainly the easiest to interpret, and it's the easiest one to compute. So it raises the question of why do this other stuff? Well, there are two big reasons, and one is that we often care about consistency of observations. If you get a small variance or standard deviation, it means that almost all the observations are pretty darn close to the mean. But a small MAD can come up when you have lots of values close to the mean, but a few that are really quite far away. We just saw that distance observations pretty far away from the mean cause a much greater increase in the variance. The other reason is one I can't tell you as much about. Variance and standard deviation have lots of very nice statistical properties. I'll be telling you more about that later, but we're not quite far along enough for me to do that right now. Okay, how about symbols? Population variance is represented by sigma squared. This is a lowercase sigma. It looks kind of like an O with a haircut. If you take its square root, you get the population standard deviation, which is just sigma. In the bottom two rows, we have a different name for the sample variance and the sample standard deviation. When working with samples, we use S, the English equivalent of the letter sigma. But I should point out right now that the formulas I just taught you are for populations, not for samples. We'll be seeing the sample formulas in class, but this video doesn't cover them. Let's give you a little practice to see if you've got these ideas down. I'm showing you here a small population on a number line, 12 observations, each represented by a block. As you can see, all of these observations are equal to the number 8, all 12 of them. I'm going to move the blocks around and be asking you some questions about what the range is, what the mean is, and what you can tell me about the standard deviation or the variance. If you understand what we've talked about, hopefully the answers will be clear. I'm going to pause only briefly between the time I ask the question and the time I give the answer, so you might want to have your finger kind of close to the pause button to see if you can answer it yourself. And my dog is trying to answer it right now. He just loves math. All right, here we go. Right now, 12 observations all equal to 8. What is the range of the data? It's 0. The biggest observation is 8. The smallest observation is 8. The difference between those two is 0. So the range is 0. What's the mean of the data? Well, that's just as easy. The balance point of this stack is pretty clearly at 8 on the number line. They're all equal to 8, and the average of those numbers is 8. All right. What's the variance of these data? To find the variance, you have to find each of the deviations, square them, then average those squares. The deviations tell you how far the data is from the mean, and everything's exactly at the mean, so every single point has a deviation of 0. Square those zeros, and they all come out to be zeros. Average 12 zeros together, and you get 0. So the variance here is 0, and its standard deviation is the square root of 0, which means it's 0 too. All right, that was pretty simple and find it kind of boring. So let's change it a little bit. I'm going to grab these 6 blocks and move them over here to 12. What's the range now? Don't tell me it's 8 to 12. Range in statistics is a specific term. It's the biggest minus the smallest. 12 minus 8 is 4. All of these numbers fit into a space of only 4 units on the number line. The range is 4. What's the mean? Don't do a calculation. The mean is the balance point of this picture. With equal stacks of equal size, the mean is going to be right in the middle of those two. It's going to be where they would balance, which is at 10. Okay, knowing that, see if you can compute the variance of this population. First, I take how far each observation is from the mean. Some are 2 below the mean, some are 2 above the mean for for deviations of -2 and +2 respectively. But no matter which way it's signed, plus or minus, when you square each deviation, each one comes out to be 4. 4 for each of these, 4 for each of these. I'm averaging together 12 4s, and the average of those, of course, is 4. So the variance is 4. And the standard deviation is the square root of 4, so it'll be 2. Notice that with these two equal stacks sitting side by side, that the standard deviation came out to be how far each stack was from the middle. That works here, but it won't work in general, so don't get too used to that. Okay, let's make one more change. I'm going to take part of this stack here, the top entry, and move it to the middle. I'll go to this stack over here and do something similar, taking its top entry, I hope, and moving it to the middle. All right. I have a new picture where I've taken the top of each of these stacks and moved them into the middle. Has the range changed? No. Biggest and smallest values are the same as they were before. Biggest minus smallest is 12 minus 8, which is 4. Has the mean changed? No. The picture used to balance on the number 10, and since I took equally from both of these two stacks, it still balances on the number 10. So the mean's the same too. How about the variance? Has it changed? And if so, in what direction? Yeah, it's changed. Before, we had 12 observations, all that were at a distance of 2 from the center. Now we have 10 observations for which that's true, but 10 observations that are right at the center mark itself. As data moves from the outside of the data toward the mean, the variance and standard deviations are going to go down. If you take data from around the mean and move it out toward the outskirts, the standard deviation and the variance will go up. Okay? Let's try one last one. I'm going to grab all of this data and then drag it down the number line. Instead of having it centered at 10, I'll have it centered at 4. See, I didn't get the last part here. Let me make sure that this comes down and joins the club. There we go. All right. Has the range changed? Has the mean changed? Has the standard deviation and the variance changed from the one that we had up here? Well, the range hasn't changed. The biggest value is 6, the smallest value is 2, and so the calculation 6 minus 2 is different, but it's still true that the biggest number and smallest number differ by 4. Dragging it down the number line didn't change that. How about the mean? Well, the mean's the balance point of the picture. The picture used to balance at 10, and now it balances at 4, so yeah, the mean has definitely changed. How about the variance? Well, while the mean has changed and the data has changed, the variance talks about the deviations of each point in the data from the mean. And the relative positions of the blocks compared to their averages hasn't changed. They're still the same distance from the average they used to be. Just when I drug it down the number line, it made no difference. So we have the same variance as we did a moment ago up at 10, and also the same standard deviation. These ideas are kind of important, and as you've seen, we haven't done a lot of calculation. We're more getting a feeling for what these things are talking about. You might want to go back over this last part of the video and make sure that you could answer the questions without me having to give the answers to you.